Hello guys. Um, I'm going to start as soon as somebody lets me know that you can see me and hear me well. So today we're going to continue our discussion about neural networks, and we're actually going to discuss in more details about deep learning and some of the concepts involved in deep neural networks. Okay, so I'm waiting for some confirmation before I can start the lecture. I should be live and you should be able to hear me now. So, okay, thank you. Maybe it's a bit more of a delay than what I expected. Okay, so yeah, just a recap. So today we're going to discuss about neural networks and deep learning. So we'll discuss a few tips and tricks for training and also some details about activation functions and training algorithms and so on. And next time we're going to discuss about convolutional neural networks. So these are specific architectures. Okay, so yeah, from the previous lecture we discussed about the loss functions of the SVM, the hinge loss and the softmax loss, which is used in the multinomial logistic regression. And we saw that softmax loss is able to provide values that are non-zero even if the example is correctly classified, but without a maximum likelihood. And we also discussed about training these models using gradient descent. So in order to employ gradient descent for neural networks, we interpret these models as graphs, and then we apply the chain rule in these graphs. So first, the gradient descent is applied with respect to the loss function, which is has an irregular surface, just as like these mountains, but now we can imagine the mountains in a 3D space. But actually the loss function is in a much higher dimensional space that is not something that we can imagine. But the main idea of gradient descent is still the same. So we are in some location on this loss function. We estimate the gradient in the vicinity, and that way we can make small steps towards a local minimum. And we hope that this local minimum is a good solution of our model. So in order to apply gradient descent, we have to compute gradients, which can be done in two ways. The numerical approach, which is based on using this estimation of the gradient using the limit function. And this provides us an approximate value, and it's very slow to compute. And we also have the alternative approach to employ calculus in order to provide a closed formula of the for the value of the gradient. So if we have this formula, we can compute the gradient directly for any input x of our function. Okay, so in practice we typically use the analytical gradients, but we can also check the implementation using the numerical gradient. And of course, if we use predefined layers or predefined architectures, this is not really required to compute gradients and so on. So this is done through frameworks that already have these implemented some of the functions. Okay, so the gradient descent is based on an update rule. So we update the weights of the model. So here the weights are denoted by this parameter W. So we start with some initialization of the weights. And today we're going also to discuss about how do we initialize neural networks and what problems can appear with different initialization approaches. And then we apply this update rule, so the weights are updated in the negative direction of the gradient. So here we have minus the gradient, and in order to make sure that our step is not too large, we just multiply the gradient with a learning rate. So yeah, this was already discussed last time. So there is also this concept of why neural networks are useful in practice. So mainly they replace methods that are based on uncrafted features, like the bag of words model, in which instead of using this uncrafted representation, the network learns also the representation inside its architecture. So it actually learns a hierarchy of features and a multi-level representation of the input, which is better suited for the problem because it is not based on the intuition of some engineer, but it is learned from data. So it is also a paradigm shift from other machine learning or the standard machine learning approach that is based on feature extraction and then classification, and perhaps, I don't know, feature selection somewhere in the middle. This is replaced with end-to-end learning. So now people have tried to employ these architectures in various applications, but the main idea is to how to use or how to design an approach that can be trained in an end-to-end fashion. So in many cases this is not that easy, and it required several years for people to propose end-to-end training pipelines. And for example, this is the case of object detection in images. Okay, so as I said before, yeah, we model the network as a computational graph, and here we have a simple graph with a network with only one layer. So the network is just a multiplication of some weights to with this input, and then we have the loss function and some regularization term that compose the final loss. And when we optimize the model, we propagate the gradients through this graph using the chain rule. So last time we had two examples with the chain rule that were explained in detail. This is one of them. So if we choose, for example, this function that we want to optimize, we just take some values for the parameters, we compute the value of the function, and then we can use the gradients, we can compute the local gradients and backpropagate them gradually through the network using the chain rule. So for a certain node, let's say this node here, the gradient of our function, so this in our case for learning models, the function is the loss, and the parameters are actually the model weights. So yeah, but for any function, the chain rule is applied by using the local gradient multiplied with the gradient that comes into this node. So the gradient back propagation is based on this chain rule. So here we can explain it actually a bit better. So here we have the local gradients. So this node has, I don't know, implements some function f. It outputs the output z. So here we have the local gradients. So the gradient of this local function with respect to x and with respect to y. And when we do the backpropagation, we will get the gradient of the loss function with respect to the output of this node by applying the chain rule. And then when we apply the chain rule for this node, we just obtain the gradients with respect to the input x is the gradient that comes here times the local gradient. And the same, we do the same for y. Once again, this is a recap from the previous lecture. So we saw that writing down the gradient formula by hand for all parameters is not really possible. So because there are many gradients to compute. And for the same reason, we do not train neural networks on the entire training set at once, but instead we use mini batches. So the training algorithm is called stochastic gradient descent. And the training is based on backpropagation, which involves applying the chain rule recursively for every parameter in the network, and then we update the parameters using the gradient descent rule. So in order to train a network, we have to first do the forward pass, then we do the backward pass, which is about twice as complex as the forward pass, because we have to compute gradients with respect to input and with respect to the weights. So there are twice the number of computations. And after the forward and backward passes, we do the update. Okay, so as we saw last time, networks can also be expressed as functions with matrix notation. So a very simple network that contains, let's say, a unit or a layer of units can be expressed as a linear function f, where we multiply the weights with the input x. And we can also go to more complex neural networks that have, I don't know, two layers. So this can be expressed something like this. So here we also saw the function max of 0 and the input. So this is an activation function. We didn't discuss so much about activation functions in the previous lecture. So today we're going to discuss more about these architectures. And we can also represent the neural networks graphically. So there are different graphical representations, or also have some variants in a future slide. So one way to represent the network with this hidden layer can be represented like this. So we have the input x, the weights w, the intermediate representation, then the weights from the second layer, and the final output. And we can go on and adding more layers into the network. So we can go to a 3-layer neural network and so on. So this function can be more and more complex. So one important aspect here is for you to remember is that these activation functions are very important for the models in order to obtain nonlinear decision boundaries. And why is that? So imagine we have this 2-layer or 3-layer neural network from which we remove the activation. Then what we can do, so instead of here now, when we have this activation, we have to compute w1 times x, then we apply the activation, and with the output we multiply it with w2, then we apply the activation, and so on. But if we just remove the activation, then we will have W3 times W2 times W1 times X. So actually these matrices are compatible for multiplication. So instead of multiplying X with W1 and then the result with W2, we can also do the same operations from the other direction. So we can multiply W3 with W2 and obtain an intermediate matrix that can be multiplied with W1, and then in the end, from this W3, 2, and 1, we will have a single matrix, let's say W star, and this matrix is multiplied with X. So from this computation, we learned that these can be compressed into a single matrix, so this becomes equivalent to learning a simple linear function. So because of this, it means that a neural network with any number of layers that does not have activation functions is actually a linear model. So it will learn a linear decision boundary. So the main reason why the networks are nonlinear or are able to learn nonlinear decision boundaries is due to the activation function. And this is why the activation is also sometimes called nonlinearity, because it introduces the capacity to learn nonlinear decision boundaries into the neural networks. So we will discuss more on activation functions as we look into we start to look into the some architectures for neurons, and we discuss how it models the biological model of the neuron. So now we make this short presentation or short parallel to the biological neuron. So our mathematical model is trying to model this cell in the brain that has a nucleus and some connections that are called dendrites, and also a larger connection that is called axon. And these ramifications are called synapses, and they are connected to other neurons. So the information from other neurons is passed through the axon. So the axon transmits information, and the neuron gets information from the dendrites. So actually this information is an electrical current. It's called action potential. So yeah, there are some electrical currents that circulate in the brain, that they pass through these synapses. They are accumulated into the neuron in the cell, and if the electricity passes a certain intensity level, then it excites the neuron, and it further passes the electrical current through the axon. Yeah, so essentially the brain works by transmitting these electrical signals, and we are trying to model this at the same level mathematically through this model of the neuron. So here we have the inputs that are these are the dendrites. So each dendrite has an input x, which is a real value. So it really, here in the mathematical model, it can be any positive or negative value. And here actually we know that the current is measured only as a positive value, but this is not really that important. So we want to work with the full scale of possible numbers. Then another thing that happens is that the brain learns some pathways for the electrical current that stimulates, I don't know, different parts of the brain. And these are learned by the brain by strengthening some synapses or by decreasing the strength of other synapses. So these ramifications can grow in size or can shrink. So this growth of the synapses or shrinkage of the synapses is modeled through these weights W. So the stronger synapse will have will correspond here to a higher weight, and smaller synapse will correspond to a lower weight. And the weights can also be positive or negative, so they have here in the mathematical model they have can have associated various values. And then all these inputs are summed up, so this simulates the accumulation of the intensity currents that come from all the dendrites. And then we also have a step function or an activation function. So after if the electrical current passes a certain threshold, then it is further passed through the axon. So this is regulated by the activation function here. And then we have the output that can be distributed to different units in our neural architecture. Okay, so this is the relation to the biological model. We also saw in the previous lecture that actually this model can be used to learn linear decision boundaries. So the geometrical interpretation of this equation is a hyperplane in this space. In this case, it has 3 dimensions, but in general, it can be in a higher dimensional space. Okay, so as the step function here, we can use, for example, the sigmoid, which we presented or used in a previous lecture in a graph, computational graph. And actually, the sigmoid is used in to model the step function in neural networks, but it wasn't used initially when the neuron was introduced. So more on this later. Okay, so neural network architectures can be represented graphically like this. The typical architecture is a feed-forward neural network that has an input layer and output layers, and a number of hidden layers in between. So the information circulates from the input to the output in the forward pass and then backwards in the backward pass. So this type of architecture is used, it can be used for classification problems and regression problems without issues, but there are also other architectures that can use feedback connections. So these are only feed-forward connections, but there are also architectures that can, for example, pass the information back to, I don't know, a previous layer. And one popular approach in this direction is called recurrent neural networks. But we're not going to discuss about recurrent networks in these lectures. We will discuss about them in the second year of your master. Okay, and these are also called fully connected layers because every unit from the input is connected to every unit from the output. So the information from one neuron from a layer goes to all the other neurons from the subsequent layer. So these are called fully connected layers. And we will see next time that we can also have layers with sparse connections. But more on this next time. So a fully connected layer can be represented in so these are actually 2 connected layers. So we have here the mapping, the hidden layer k and hidden layer k plus 1. So we can represent these fully connected layers like this or like this. So here we see that this is multiplied with some matrix of weights, and then we apply the transfer function or the activation function. This is another way to represent the same configuration. And also here we have the detailed fully convolutional layers, where we see all the possible connections in the layer, but it's not always graphically designed like this. So there are various graphical representations for neural networks, but in the end they all mean the same thing. And yeah, last time we also presented an end-to-end neural network for the XOR problem, just to prove to you that neural networks can solve nonlinear decision problems. And for simplicity here, we introduced the bias term into the input X. So the third component here, 1, represents the bias term for the neuron. So maybe I forgot to mention here that each neural cell can activate at a different level of the electrical current. And to model this mathematically, we need this bias term, which in geometrical interpretation, it gives us the possibility to shift the hyperplane from the origin. Okay, and we trained this network, and we saw that it can reproduce the XOR output. So we can also represent graphically this neural architecture for the XOR. So one of the inputs here is considered the bias term. So it's here, since we have full connections and we have 3 units and 4 output units here, the corresponding matrix of weights has 3 rows and 4 columns. And here we have only 1 output unit, and all these units here are connected to it. So we have 4 rows for the 4 inputs and 1 column for the 1 neural unit. So here we know that this is the sum. So this is where the electrical current is summed up, and here we have the transfer function of this unit. So the neuron is actually represented here like through these joint components. And typically we can also represent neural networks, so the bias term like this, but actually this is a mistake. So here the bias should be yeah, actually the representation is not right. So just maybe just use it like this. Yeah. But oh no. So yeah, this was a small mistake here. Okay, so okay, so the number of layers and also the number of neurons influences the capacity of the model. So as we add more neurons and more layers, our network can learn a more complex decision function. So for example, a model with 20 neurons can learn to separate this data set into green dots and red dots. And the recommendation is to use networks with higher capacity and a larger number of layers, but to reduce the capacity of the model by using regularization. So instead of reducing the model capacity, we try to increase the regularization until we obtain a good optimum of the model. So when we increase the regularization, we obtain a smoother decision boundary for our neural network. Okay, so a lot of the time spent into training neural networks is finding the right architecture, which means finding the optimal number of units in each layer and the optimal number of layers. And we also saw that we can use efficient matrix multiplications in order to compute the output and also to do backpropagation. So we obtain typically better results with bigger networks, but we have to also include more regularization into the model, so to use sufficient regularization. And of course, this works better if we have also enough training data. So this is also related to the amount of training data that we have at our disposal. So next we discuss about a few aspects that are involved in training neural networks, so assisting the training process. We start first with a bit of history on the training algorithms that were proposed for these models. So the first model of the neuron was introduced by Frank Rosenblatt in 1957. So more than 60 years ago, this model is called a perceptron. So it's actually the neural model that I presented previously. The only particularization for this model, so the only new thing to introduce now is that the transfer function is based on this decision. So if for one side of the decision boundary, we output 1, and for the other side we output 0. So this is like the sine function, only that it has 1 for positive values and 0 for negative values. So it's also known as a hard limit function or hard lim. And the update rule proposed by Frank Rosenblatt is based on this update. So we modify the weights by multiplying. If the prediction and the target is okay, then the update the weights stay the same. Otherwise, if there is a difference here between the target and the prediction, then we update the weights with the learning rate, this difference, and also multiplied with the input x. So this is the update rule that was proposed by Frank Rosenblatt. It works as long as the data that we have to classify is linearly separable. So if there is any data point that is not linearly separable by this model, then the perceptron will not converge to a solution. So we must make sure that the data samples are linearly separable. And actually, there was a hardware implementation of this Rosenblatt perceptron. It's called the Mark I perceptron. And the implementation was actually a machine that is connected to some sort of a camera that was was able to display images or to form images on a 20 by 20 pixels. So they had some photocells. So this produces a 400 pixel image. that is provided as input to this model. Yeah, so we have this machine in this picture right here to just to give you an idea of how it looks. And later, Widrow and Hoff in about the 60s proposed a similar machine called Adaline. So this was short for adaptive linear element. So it's a similar idea. Here they had the update rules here are actually based on gradient descent. But in order to apply gradient descent, they apply it before the transfer function. So they have this sine function that it is implemented through a quantizer that provides the final output 1 or -1, and the weights are computed with respect to the output taken from this point of the network. And since here we do not have this continuous transfer function, we can compute gradients and we can apply gradient descent. So here the function, there are two problems with this function and this function here. So this is a constant function, so and it's not continuous, and being constant the gradient is equal to 0, so it is not possible here to apply gradient descent. And also here we cannot apply gradient descent, so because here the gradients are equal to 0. So this model is trained using gradient descent, so the update rule looks something like this. So it is pretty similar to the update rule used by Frank Rosenblatt, only that the actual y here doesn't contain the quantizer. And actually this is derived from the gradient. So the loss function that they used is the sum of squared errors, and when you compute the gradient with respect to w for this function, so here w is replaced with this, and we extract the gradient, so we replace here y, and we compute the gradient with respect to w, and we obtain this value here. And the same for b. So actually the gradient, if you use here the power, the gradient will be something like 2 times this thing. But actually, if you optimize the function multiplied with 1 divided by 2, then you will eliminate the need to use 2 here. So it's an equivalent notation. Sometimes you will see that the loss function is without 1 divided by 2, and then you will see that the update rule is 2 times the learning rate, and so on. Okay, so yeah, this is the other line, and then in 1986, Hinton popularized the backpropagation algorithm, and people started using neural networks. And in order to use neural networks and to use backpropagation through the entire model, they also had to replace this quantizer that had gradients equal to 0. So since the gradient here is equal to 0, when we do the update, actually the gradient, if the gradient is equal to 0, there will be no update to the weights, so this is problematic. And also the function is not continuous, so we had to replace this in modern architecture with other activation functions that have non-zero gradients. So the first strong results with deep neural networks appeared in 2010 and 2012 for speech recognition and image recognition. So in the 80s we had results, and people were working with two-layer neural networks, and since 2012 people started using deep learning, and these have become more popular in the field. Okay, so an overview of the training. So in order to train models, we have to take care of different things. So first, there is the initial setup. So we have to choose the architecture of the neural network. So here we have to decide on what activation function to use, what preprocessing is applied on the data, how do we initialize the weight, what type of regularization, or if we use regularization, and so on. So this is the required as a one-time setup. But of course we can change the activations or the way we initialize along the way, as we also change the architecture of the model. But this is set up before starting the training process, so we usually do not modify these components during training. Then we have the training process. They actually when we apply gradient descent. So here we have to follow the value of the loss during training, see how it decreases, see if we need to do some hyperparameter adjustments, and so on. And finally, we're also going to discuss about model ensembles, which can improve the results, so neural network ensembles, and also about dropout. So this is the plan for today. I hope we can pass through all the things that I want to discuss with you. Okay, so just checking if there are any questions so far. So far, so good. So yeah, we're going to discuss about the activation functions. So the activation function is this function f in this graphical representation here. So we can use different activation functions. So recall that in the Rosenblatt perceptron, we had this hard limb activation function. So in order to have a continuous function through which we can backpropagate gradients, this was replaced with the sigmoid, which is 1 divided by 1 plus e to the power of minus x. Here we also have the quantizer used in other lines. So this is, but the continuous version is called hyperbolic tangent. And there are more modern options such as ReLU or variants of ReLU like leaky ReLU and ELU. And other approaches are maxed out, and so on. So these are not these are perhaps the most popular activation functions, but these are not the only ones. There are others, of course, in the literature. Yeah, and we're going to discuss about each activation function and see what are the advantages and disadvantages. So for the sigmoid, it squashes the numbers to the range 0 and 1, and it is historically popular because of the Rosenblatt perceptron. So it has more connection to the biology, but it has three problems. So the neurons that are saturated kill the gradients. So what this means is if we have this sigmoid gate, so the function here is sigma, if the input x is close to 0, so it's somewhere in this region, the output will be 0.5. So the output will be somewhere in this region. So here we will have a gradient that tells us the function is increasing, so that we will have a positive gradient. But if we look at minus 10 or 10 in this region, here the function is almost constant, and also the same here. So since the function is almost constant, the gradient will be very, very close to 0. So this is problematic. So it means that if the input x saturates to one of the two, so the goal of training is to move the input towards one direction or the other. So when it starts to approach this region, it will saturate, and the network will no longer update, or this unit will no longer update its weights. So the local gradient will be equal to 0, and consequently also the gradient with respect to the input x will also be equal to 0, or very close to 0. And then all the units before this node will no longer be updated. So this function, the problem is that this saturated neuron can kill the gradient, so the network will no longer update. So this is one problem with the sigmoid. Another problem is the outputs are not zero-centered, and we are going to discuss about this in this slide. So what do you think happens? So imagine if we have this linear model. We have the activation function on top, and we think about the input x, which is always positive. So the input so the input comes from a unit that is always positive. So when we compute the gradients, for example, on W, what do you think happens? So this is a question for you guys to answer. Perhaps, I'm not going to insist too much though, because it's not so easy to figure out. So we have a question: are there situations in which you want to have the label 0? Yeah, so there are situations when you want to make the labels like that. So this is a good observation, because the network, so usually a sigmoid is used in the last layer of the classifier. And if you use hard labels like 0 and 1, it is hard to learn the model through the end. Yeah, so yeah, actually I forgot to say one thing. So perhaps I should use this as introduction. So I think Lida, you're the only one in this situation, so you already have the full point for the lectures from all your answers. So now your answers are for free, so you can no longer get points. So perhaps you can leave other students to answer, so that they can also own points. Okay, so going back to your question, yeah, so instead of using these hard labels, you can use these labels like 0.2 and 0.8. And it seems that you can train models, you can train better models if you use this idea. And yeah, it's called, I think the idea is called So in order to train like this, you use a parameter that is called the temperature, and the idea is called dark knowledge. So yeah, you can read more about this this is an answer for Smith 1. You can read more about dark knowledge and neural networks if you want to learn more about your question, but it makes sense. Okay, so okay, going back to the question. So yeah, the Lida's answer was right. So the gradients are either always positive or always negative. So imagine if you have the optimum. So these are the regions in which you can have the gradients. So in these directions. And yeah, if you have the direction that you want to go is in somewhere in the fourth quadrant or the second quadrant, then your update will have a zigzag path because of this sigmoid. Okay, so yeah, one way to solve this problem is to make sure that the input data has zero mean, which means that the input x will have both positive and negative values. And more about initialization we'll discuss after the activation functions. Okay, so the third problem with sigmoid is that it involves the computation of the exponential function, which is a bit computationally expensive. So other activations like the hyperbolic tangent this one solves the problem with the zero-centered output. So since the output is zero-centered, we don't have this problem of the convergence with zigzags because of the signs of the gradients. So yeah, it improves on the convergence time, but there is still the problem with the gradients that get saturated. And a more recent proposal, so this is also historically motivated, it was proposed in the 90s, and in 2012, when AlexNet was applied on images, it was also the first application of rectified linear units as activation functions. So it was a bit surprising at the time because the function is not continuous, and it is continuous, but it's not derivable in all points. So we do not have the derivate for x equals 0, but still they were able to use this function to train neural networks. And the main advantage is that it does not saturate on the positive side. So no matter how high x is, you will still have a positive gradient, so you can continue to optimize. It is very computationally efficient, so it does not involve computing exponential and so on. And because of this, it converges much faster than sigmoid, usually about 6 times faster. And it still has this disadvantage that the output is not zero-centered. So it has the same problem with the sigmoid, so it converges in zigzag. And Another problem is that for the negative side, so if x is negative, the gradient is 0. So this means that the unit will not be able to update if the input is negative. So yeah, for 0 we can use the gradient equal to 0. For negative values we have the gradient equal to 0, and for positive value the gradient is equal to x. So it's a pretty simple unit. The problem is when we initialize our weights, if it happens that when we have all the data points multiplied with the weights, with our initial weights, if all the output is negative, then this unit will never activate. So this part of the network that contains this ReLU will not update. So we have to be careful with the initialization of the network in order to avoid having inactive ReLU units. So in order to avoid this problem, people typically like to initialize the weights with slightly positive biases for the ReLU, but only very small. Okay, so another way to avoid this this problem of inactive ReLU is to use this updated version, which is called leaky ReLU. So the initial version was proposed in 2013 by Maas. So the idea is that for the negative side, instead of making the output equal to 0, we just multiply it with a very small positive constant. So the function looks something like this. So it has the same benefits as ReLU, only that the gradients will not die for the negative side. So we will have some small gradients here, and the unit can is never inactive. So it can work better than ReLU in some situations. And we also have this version introduced in 2015, where for the negative side we replace this value with a parameter that is adjustable. And in more recent developments, this can also be learned, so it can be a parameter of the network that can be optimized. Okay, so this is optimized with back propagation, so it is automatically adjusted. Okay, another approach. So all these have a slight bias towards the positive side. So in order to eliminate this bias, in 2015, Clevert proposed exponential linear units, or ELU for short. So the function looks something like this. So it is for the positive side it is equal to x, but for the negative side it is multiplied, it's the exponential -1, so which has this function of same shape as the exponential, only that is shifted with 1. So it provides closer to 0 mean outputs. This parameter is also learnable through backprop, and the only disadvantage is that the computation requires the exponential here, so it's a bit slower than ReLU. Okay, another idea was proposed by Goodfellow in 2013. where they introduced the max out neuron. So it's can be interpreted as a generalization of ReLU and leaky ReLU. So instead of um, using um, like two network branches that compete against each other. So here we have this set of weights and this other set of weights, and these compete among each other, and we choose the maximum of the components. So each component from here and each component from here is compared, and we take the maximum among the two. So this is just like using I don't know, here, yeah, two different weights for the same input x. We obtain some values, and then we compute the maximum of that. So it's it's a generalization of ReLU and leaky ReLU. So instead of having max of this and 0, instead of 0 we have this component, which can have any shape. The only problem with this approach is that it doubles the number of neurons. So here actually, yeah, it doubles the number of weights, so it's a bit more computationally intensive. Okay, so for short, in practice, we typically use ReLU nowadays. If our network, so if we have problem with convergence or we have inactive units, we can try leaky ReLU, parametric ReLU, and so on. We can also use the hyperbolic tangent, but perhaps without too much expectations. It may be more useful in layers with full connections, and also sigmoid is not typically used inside the architecture, perhaps only at the prediction layer. When you want to make predictions between 0 and 1, it is useful to use the sigmoid there. Okay, so this ends the discussion about activation functions. So now we discuss a bit about the data preprocessing. I'm also looking at the time to make sure that actually I have to check maybe the number of slides. Okay, so I think I'm somewhere halfway, so probably I have to take less time for the remaining part. Okay, so in order to make sure that the data that we do not have this zigzag convergence with units that do not produce zero centered output, we can normalize the data by shifting the center to the origin. So this is done by computing the mean and by subtracting the mean from the data. And then we can also make sure that the variance on all axes, or the standard deviation, is equal to 1 on all directions. And this is done by, after shifting to the center point, we compute the standard deviation and we divide each data point by the standard deviation, then we obtain the normalized data. And these are actually the Python commands to normalize your data, assuming that the data, we have one sample per row, so the data has this dimension. Okay, so in practice, for example, when we do image classification with convolutional neural networks like AlexNet, it is a common practice to compute the average image over the data set and subtract the average image from the input. For VGG, they done a simpler idea, which is compute the average for each channel RGB and then subtract this value from every pixel in the image. So instead of having to memorize the average image, we have to just memorize 3 value for the RGB color channels. And for more recent architectures like ResNet, it is not mandatory to normalize the data. And this is because these architecture contain layers that normalize the data as it passes through different layers. And this is done using an approach called batch normalization. And there are also variants of batch normalization like instance normalization or adaptive instance layer normalization and so on. So when you use batch normalization, you can avoid normalizing the data, and you will figure out why when we discuss about batch normalization later today. Okay, so one important aspect is also initializing the weights. So what do you think happens when we set the weights equal to 0 for this network? So assuming that W is equal to 0, what will happen? Okay, so the gradient will be 0 and the network cannot learn. That's correct. I assume this is so maybe Armand, can you give me your full name so that I can add it to know who to give the points? Okay, so yeah, we have the answer. So instead of setting the weights equal to 0, in order to ensure convergence, we have to initialize the network with some random values, but we also have to make sure that these values, if they are, I don't know, very far, if they have high values, and if the network is very deep, we can have problems with the gradients. So either the gradients can be can explode. Actually, they can have very very high values, and usually this is so for small networks it is okay to initialize the weights with from a normal distribution of 0 mean and standard deviation 0.01. For larger networks, we can use this approach, which is called Xavier initialization or Glorot initialization. So the name of the approach comes from the first author of this paper from 2012. Yeah, so if we choose the initial weights are too small, then the signal strength propagated in the network drops with each level. So because recall that the network is a composition of functions, so it's just multiplying several values there, and as you have more layers you will have more numbers to multiply. So if the weights are very small, the output will drop and probably can even go close to 0. So the gradients can actually vanish and become equal to 0. And also the opposite can happen. So if the weights are too high, the signal strength propagating in the network can become very, very big and can explode, which means that it overflows the number of digits for float or double and so on. So to solve this problem and to make sure that the weights have the right magnitude, we can take into consideration the number of input units and the number of output units. So the idea proposed in this paper is to initialize the network from a normal distribution of zero mean, and for the standard deviation we use this formula that is given by 2 divided by the number of input units plus the number of output units. So we have for each layer we have a specific number of units, and we'll have a different standard deviation. And actually in modern frameworks we have this type of initialization. So we just have to specify, use Xavier initialization or Gloro initialization, and the network will be automatically initialized for you. And this is still an active area of research, so there are different papers on this topic. So yeah, this is the paper from Gloro, but since then there are also other papers that study this problem of network initialization. And another solution for the network to make sure that we do not have exploding or vanishing gradients is to use batch normalization. So what batch normalization does is we take the output from some layer of the network, and we normalize the output. So we take the output, we compute the mean, we subtract the mean, we divide it by the standard deviation, and we obtain a different set of activations, a different output that is normalized. So the main idea is that, okay, if we want to have unit Gaussian activations, ideally, so we just make them so. So this is the main idea. If we want to have values that are not too small, too close to 0, or too big, we just normalize them to make them in the right range. So this is the idea behind the batch normalization. It is important to note that the mean and the variance is computed independently for each dimension. Yeah, this is done let's say feature-wise. So yeah, we compute this mean and the variance, then we normalize the data, and this is typically inserted before the activation function, and it was used in ResNet models before the fully connected layers, but before the TANH activation. And after the normalization, another step is to allow the data. So if the network wants the data actually to be in a different range, then we have some parameters, gamma and beta, that learn to reproject the data into the desired range of values. So it can actually even learn to recover the identity function. So if this operation is not useful, then the network can learn the parameters, the mean, can learn a new standard deviation and a new mean and can actually shift the data back to the original output if required, but it can also shift it to a different range. It depends. So these parameters are learned from the data, so they are optimized with the model. So yeah, and putting together all the steps for batch normalization, it looks something like this. So the main benefits is that batch normalization improves gradient flow through the network. It allows us to use higher learning rates so we can make faster updates. It reduces the dependence on initialization. So even if you don't initialize the network so well, it can still train the network because it automatically adjusts the output to the desired range, even if the initialization gives, if we get bad values due to initialization, it can still work quite well. Okay, and actually batch normalization can also work as a form of regularization. So it's just as in linear models when we want to make sure that weights have a certain norm. So here we can regulate the norm of the weights by making sure that the input has values in a certain rate. So it's a kind of indirect regularization. And it also reduces the need to use dropout, but more on dropout at the end of the lecture. So we're also going to discuss about dropout. Okay, and one important aspect here for batch normalization is what happens at test time. So when we train the network, for each mini batch, we have to estimate the mean and the standard deviation over the mini batch. As you see here, we have the input x, so we have the values of x for the entire mini batch. Well, at test time, we do not have mini batches. So at test time, we have only one data sample that needs to be processed. So this is typically done by estimating an average and the standard deviation during training that is going to be used at test time. So you have to make sure that when you use batch normalization at inference time, not to leave the network to compute the mean and the standard deviation for the batch norm layers from the test data, because it will not provide good results. So at test time, these values have to be frozen and to be pre-computed. So make sure that if you use batch normalization, be careful with this, with these parameters not to be computed from test data. Okay, so next about the learning process. So we discussed a few things last time about the gradient descent. We're going to redo this discussion in depth. So first, about babysitting the learning process also involves choosing the right architecture. So this means choosing the number of units on each layer, the number of layers, the type of activation for each layer, and so on. And in practice, in order to make sure, so once we have this architecture set up, we first make sure that the model can produce loss values in a reasonable range. So for a classification task, for example, with 10 classes, we expect a reasonable loss to be around 2.5, so this with random initialization. So yeah, we assume that the network for 10 classes can estimate 1 in 10 examples, and if you compute the average loss should be somewhere around this range. Okay, so the initial loss should be somewhere around 2.5, so this is for the cross entropy loss. Then when you add regularization, we expect the loss to increase a little bit because of the regularization. And then we also have to make sure that the model has sufficient capacity to learn. So we can, for example, make the network overfit on a subset of the training data, like 20 samples, just to make sure that we can train the network to overfit. And yeah, these are the preliminary steps in order to make sure that the model is configured correctly. And then we start training the model, start with some small regularization, and add more regularization as needed, and also decrease the learning rate, and see when the network starts to converge. So these are also hyperparameters in the network, the learning rate, the regularization, that can be optimized using random search or grid search. Grid search means just, I don't know, using, let's say, for options for the mini batch size, 32, 16, I don't know, 8, and maybe 128. And for another parameter, let's say the learning rate, 10 to the power of minus 2, 10 to the power of minus 3, and so on. So in grid search, it means that we try out every possible combination for our parameters, and we keep the model with the highest validation accuracy. And for random, we can also do random search, and it was studied in this paper in 2012, and it was shown to produce slightly better results than grid search. And instead of using these fixed values, here you can actually use, you can test out different values, and you can also look for how your performance is going, and try to actually find some optimal range for your parameters, and then you can try more values in the optimal range instead of trying to use values on a regular grid, as in grid search. Yeah, so the hyperparameters that you play with are the actual architecture itself, the learning rate, the update rule for the algorithm, the regularization type, and so on. So your work looks something like a disc jockey that is trying to fine-tune this to make music that sounds well. So in the same way, you're trying to fine-tune the network in order to produce the right output. So yeah, during training you have to babysit the learning process. So this means that you have to monitor and visualize the loss curve. And you will see that this is also, for example, related to the learning rate. So for very high learning rates, the model can diverge. And for optimal learning rate, it can decrease something like this. But a more aggressive observation here, instead of just using only one learning rate towards the entire process, you can use higher learning rates at the beginning because the model will converge faster. and then try to decrease the learning rate as you go along the way. If your loss function decreases like this, one possible problem could be due to the bad initialization. So if you see your loss looking like this, perhaps you can play with the initialization, or try to add batch normalization, or normalize your data, something like that, in order to make sure that the network converges right from the beginning. Okay, and you can also visualize the accuracy on the training and the validation. And typically you expect a bit of overfitting on the training data. So a bit of overfitting is okay from your model. But if there is a very large gap between training and validation, then your model perhaps is doing too much overfitting. So you need to increase regularization in order to improve validation performance. And if the gap is too small, perhaps you can increase the model capacity to see if you can further improve the results. So in summary, we discussed about the activation functions, about data processing. So it is recommended for images to subtract the mean, especially if you don't use batch normalization. For the activation function, we commonly use ReLU. For weight initialization, it is recommended to use Glorot initialization. We recommend batch normalization, and try to do hyperparameter optimization by random sampling, and so on. So now a bit about the training algorithm. This is another decision when you train your network, is to choose the right training algorithm. So there is the basic stochastic gradient descent, but there are also approaches that converge faster and in various cases you can use different algorithms. So you can see here in this graph that some, for example, overshoot the local minima, but they then slowly converge back to the minima. So we have time to discuss about another algorithm, the gradient descent with momentum. So recall this was the slide for gradient descent. And here the update rule is based on multiplying the gradient with a learning rate. And the problem with the gradient descent, so this is a question for you, I'm waiting for the answer. So we have this loss function that has a steep on the vertical axis, that has a steep descent in this direction, and shallow descent on this other direction. So try to imagine how the gradients look for this function. So this is a 3D function. This is the optimal point. And imagine how the gradient descent will optimize on this surface. Okay, so thank you, Armand, for letting me know. Yeah, so it will move left and right like a zigzag, yeah? So the gradients, so for this direction, since the function is decreasing very slowly, the gradient will be small. Here is decreasing faster, so the gradient will be higher. So here it will have a large step in this direction and a small step in the other direction. And actually here it will go to the other side. So from this part it will move on the other direction. while for this horizontal direction it will still make a small step. So it will optimize, it will go through these points, and overall the progress is slow along the flatter direction, and it will jitter along the steeper direction. So it will jump from one side of the function to the other. So in order to solve this problem, one idea is to use stochastic gradient descent with momentum. So this solves the problem, but and it is useful to escape local gradients. So it has two benefits. I opted for stochastic gradient descent because it is a very simple algorithm compared to the others, and easy for you to understand, and also because it is commonly used to train deep models on ImageNet. So you can obtain state-of-the-art results on ImageNet using stochastic gradient descent with momentum, and it is still being used for this today. Okay, so yeah, in gradient descent with momentum, the update rule looks something like this. So the weights W are modified with this component V, and here V stands for velocity, and the velocity is computed as the gradient, the negative gradient multiplied with the learning rate, and we add to V the previous value of V, which is multiplied with a factor that damps actually it models the friction on a surface. So gradient descent with momentum is similar to having a ball rolling down on the loss function, and when the ball rolls down, it has this inertia. So the inertia is given by this component here, but we also take into account the friction. So the inertia is multiplied with this parameter that is lower than 1. So because of the friction, so the ball is supposed to roll down, and because of the inertia will go up here, but also because of the friction it will gradually slow down. So for this parameter, so we have a new parameter here that we can also optimize during training. So, and it can also be modified in time, so it can start from 0.5 and can be slowly increased to 1. But typical values, typically good values, are around 0.9 or 0.95. Okay, so this new component allows the velocity to build up along shallow directions, and it damps in the steep directions due to the quickly changing sign. So going back, yeah, maybe go back to this figure here. So since here on this direction we are making small updates in the same direction, so this will build up inertia and will increase the steps, where for the other direction, so here we'll have the inertia in this direction. So when here we have the gradients to the opposite direction, and when we consider the previous update, this will cancel out and will make a small update in this direction. So in the end, gradient descent with momentum will speed up the optimization for the horizontal direction, and will decrease this zigzag effect on the other side. Yeah, and also because of the inertia, it overshoots the gradient. So it builds up on the momentum, it overshoots, but then can still recover, and in the end it converges faster than gradient descent. Okay, so before going on to this slide, I'm going to show you this example with gradient descent. So this is a continuation from the example shown in the last lecture. So here we have the same function as last time, the derivative of that function, which is here, and we have the implementation of gradient descent with momentum, and here it is just so here we have the update rule for the gradient descent, and the momentum component which is added here. So we have mu multiplied with the previous update, and the previous update is just measured as the previous x minus the older one. So for the first step of the algorithm, this component will be equal to 0, and for the others it will build up to a certain value. And we start from this location 2.5. We have the learning rate set to 0.1 and the parameter mu equal to 0.95. And when we run the model, so it starts from here. So remember, with gradient descent, so if mu here is equal to, let me just quit this. So if the parameter mu is equal to 0, then we have the basic gradient descent, and you see that the gradient descent converges to this local optima. But for gradient descent with momentum, so if we have the momentum component, because of the inertia, it overshoots the local gradient, and it goes to this region here, which is a better optimum for this function. Okay, so this means that gradient descent can escape some local minima, and it is also able to converge faster because this explanation that I provided previously. So yeah, let me just, so yeah, I quit. Yeah, so I'm going to include these examples with the slides, so you can play with them and see how it goes from different locations. Okay, so all these algorithms have a learning rate, and as I explained from this graph before, a good idea is to decrease the learning rate over time. So for this region, I would like to decrease using a higher learning rate. Then for this region, I would like to use a smaller learning rate, and from this last part, I would like to use even lower learning rate in order to achieve the greatest decrease for the loss. So there are different schedulers and how you decrease the learning rate. So one approach is to use step decay. So you decay the learning rate by half every few epochs. There is exponential decay, and here t is the number of iterations. So you compute the learning rate at the current time t by multiplying the initial learning rate with the exponential of minus k times t, and k is a parameter. We also have one divided by TDK, and so on. There are different ways to decrease the learning rate. Okay, and now we reach the last part. I'm thinking maybe, let me see if, so this is just a few slides, maybe just do it today because it's not so long. So yeah, model ensembles. So one way to improve performance with independent models is to train multiple models. And why is this relevant? It's because when you train a neural network, you do some initialization, and then when you train it, the samples are chosen in a random order. So when you do the optimization, you will reach a certain model that goes to a local optima that is not necessarily the best model that you can obtain. And if you retrain the model and you reinitialize it, you will almost certainly reach a different solution, so a different local optima. So each time you retrain the model, you obtain a different one. So a good idea would be to train several models and to use it into an ensemble. So just using a voting scheme, for example, in order to decide the final labels. So usually this gives you a performance boost of around 2%. You can even obtain this boost by training a single model and using different checkpoints of this model. So a different checkpoint is a model frozen in time, so at a certain iteration. So let's say, for example, you train the model for 100 epochs, and you save a version of the model after 80 epochs, another version after 90, and one after 100. And when you combine all these models, you can expect a boost of performance just because these models are not identical. So you can also do an ensemble like this without having to train multi-model models. Just train one model and save different versions during the training process. Okay, and this is also a bit related to dropout. Dropout can be regarded as an ensemble learning approach, but was typically proposed as a regularization method. So the idea for dropout is to just short circuit some part of the network. So some units are simply dropped out. So the weights of these units are replaced with 0, so they do not influence the final output of the model. And you might think, okay, why is this a good idea? If I remove these units, why don't I just use a model with less units and that's it? Why do I need dropout? Well, actually, this is not done just in a fixed way. At every mini batch, you actually choose a different set of units that you drop out. So it's not always that you drop out the same units every time. You randomly chose them at every iteration. So in the end, you train the entire model, not only part of the units. And the idea is to have a redundant representation of the input. So with this representation, for example, you can obtain sparse representations of the input that can lead to a good score. So one explanation here is, okay, I have these units that recognize some object attributes that are then used to classify objects. And suppose that I have some bias in the data, and the only animal that has claws in my data are cats. And then my model will classify, when it sees some clause, it will classify it as, I don't know, as a cat. So, well, what you can do to improve the model, or to make sure that it also relies on other features, like cats are typically furry, they have a tail, they have ears, and so on. Then what you can do is to remove, let's say, these units that influence the model. And in this way, you force the model to also take into account other features, and to learn an alternative representation of your object. So it will try to predict the object class by using a different set of features than it would usually do. Okay, so in the end, when you train the network like this, it will be able to make more robust predictions. And another interpretation of dropout is that you're kind of training a large ensemble of models with shared parameters. So each, for example, in this image, we have this model that we train. Then when we re-choose the units that we drop out, then we have a different particular model that we train. And then when we train all these models together, you kind of jointly train them all together. So this is the relation to ensemble models. And yeah, this is just what I said before. Okay, so what do we do at test time? We want to integrate out all the noise. So this can be done either by doing the same as in training time, but it will take probably more time to do. So you just make several forward passes and then compute the average prediction. So this is just like a normal ensemble. But a more simple approach is just to activate all the units. So essentially at test time, you remove dropout, and you leave all the input neurons turned on, and this gives you like an estimation of the ensemble model at once. And yeah, this can be shown to be a good approximation of the whole ensemble, and you obtain about the same results. Okay, and for deep learning, I would recommend you these books, Deep Learning by Jan Goodfellow and Joshua Benjo and Aaron Kurville, which you find for free on the web. And there is also this book from O'Reilly, so I can share a version privately with you if you ask me. Okay, so yeah, this was the last part. I'm glad that I managed to finish in time. And let's see if you have any questions here. Okay, so we have two answers for today, for Armand and Andrei Florescu. Okay, so just wait maybe 1 or 2 minutes if you have questions. Otherwise, Thanks for participating. Next time we're going to discuss about convolutional neural networks. So that will end our discussion about supervised models, and yeah, next in 2 weeks from that we will start the discussion about unsupervised models until the end of the semester. Okay, so it seems that there aren't any questions for today. So once again, thank you for participating and see you next week.